Okay, what is the Fourier Slice Theorem? Sorry, not transform, theorem. The Fourier Slice Theorem is page 13. This is the theorem. Actually, here, like, they show the conclusion first, and the proof comes later. So, okay, before talking Fourier Slice Theorem, we define two equations first. And then we will see these terms a lot later, so please remember this in your brain. So first, this P theta R, this is a projection we take on a line with angle theta. So, okay, this is projection. Okay, and then we define a CTFT, continuous time Fourier transform of P, and then we define this as a capital P. And this is a 1D Fourier transform. And second, we take a 2D Fourier transform, continuous space Fourier transform of fxy. fxy is the original image. Then we define the 2D Fourier transform as a capital F, FUV. And then the Fourier Slice Theorem tells us then this relationship satisfies. This is a very simple equation, but it means a lot, and it's very confusing. But I will explain it using the diagram soon. But the Fourier Slice Theorem tells this capital P theta rho equals FUV in polar coordinates. By the way, here, this equation using the term rho, this is just a frequency variable. It's very common to use small f for this, usually. But in this material, f is already used to denote the original image, so it's confusing. So just they are using rho instead of f. So this is frequency variable. So okay, what does this equation means? Actually, it's much easier to understand this equation using a diagram. So here's the diagram I drew before the class. Okay, first, we are thinking about this side first. So this is a plot of fxy, original image. And then I'm considering the line with angle theta. And then I take projection, and I call it P theta R. And then we take a 1D Fourier transform of this signal. Then we will get something. We will get some 1D signal, like as a Fourier transform of this. So it's denoted by capital P. Okay, in the meantime, let's forget about this. Okay, let's go back to my original image, fxy. We take 2D Fourier transform. Then we get some plot of FUV in frequency domain. And Fourier Slice Theorem tells us actually these values exactly match to the value on the line here, on the line with angle theta. So if we get FUV, if we draw a line with angle theta, these values on this line is exactly same as this Fourier transform of the projection. This is a little bit mysterious, but it is. So this is same. These values on this line exactly match to these values. So actually, if we slightly change the theta and just we do same thing, we can plot values on this FUV coordinate. So that means we can calculate the values on FUV. So actually, if we can take inverse Fourier transform, actually we can reconstruct fxy. Does it make sense? Yeah, so, okay, let me draw one sentence. So summary. The Fourier transform of projection p theta. Sorry, this is small p at angle theta is a slice of FUV. Through the origin at angle theta. So this is what Fourier Slice Theorem tells us. Actually, if we write down the theorem, just this one equation, but what it actually means is this. And I think it's easier to understand it through the diagram. Okay, so actually next 2 pages explain about the proof of this Fourier Slice Theorem. And actually this material shows 2 different proofs. And the first one is just plug in, and you can do it method. And the second proof is more simpler and more compact. So I will do quick review of the first proof, and then I will move on to the second proof. So page 14, this is proof number 1. Okay, so what you need to do is just plug in. So first, by definition, P theta r can be described like this. We already saw this equation in the previous note. Just definition of the projection. And then next we take a CTFT of this P. So this line is just we apply the definition of the CTFT. And then what we do is just we plug in this equation to here. And then we can get this equation. And then from here, just we swap the order of each term. And then we can get this equation. And then from this line, what we want to do is actually we want to change the variable ZR from ZR to XY for the proof. So we use the relationship equation between XY and RZ. And actually, to change the variable of ZR to XY, we need to use calculate the Jacobian here. And actually, A theta is just a 2 by 2 matrix, so it's relatively easy to calculate this. But just in case, let's calculate. Y Jacobian equals 1. So right now, okay. We have this relationship, and okay, A minus theta is minus theta cosine theta. So basically what we want to calculate is dl dv. We just want to calculate this part. And then if you look at the calculus book, like the definition of this is basically like this. And then actually, because we already know this matrix, so R and Z can be expressed as a function of X and Y here. So we just need to take a derivative here. Then we can get very simple equation. And then just take a determinant, and then you will find this equals to 1. So calculation is not so bad. This is because 2 by 2 matrix. Okay. So okay, we knew that Jacobian is 1. So just we change all of the variables from RZ to XY, and then I think most of people are familiar with this form of this equation. This is a Fourier transform. So this is a Fourier transform of fxy, but just x, this u v value takes a value rho cosine theta and rho sine theta because of this. And this is the end of the proof. So this is the first proof. So basically what we need is just keep plugging the variables. And actually the second proof is more compact, simpler, and maybe more beautiful, probably. If somebody asks you to prove the theorem, maybe you might want to use this one because it's easier. Okay, this is proof number 2. So this one, just we prove one of the case of the Fourier Slice Theorem. So we consider the case theta equals 0. Okay, if we consider theta equals 0, then projection can be expressed as this form. The reason is like this. Okay, right now we are consider theta equals 0. Okay, theta equals 0. So we have an object. So actually this is x, this is y. But we are considering the line with angle 0. So this axis R, actually it's same as x. So that's the reason why x is replaced with R. And then we take a projection along y-axis. So we are taking actually integral over y. So for the theta equals 0 case, projection equation is simplified like this. Then we take a Fourier transform of P. This is just a definition of Fourier transform. And we plug in this equation to here. And then we reach this form. And actually, again, we are familiar with this form. This is a form of the Fourier transform of fxy. Actually, R is a dummy variable, so it can be anything. It can be x, it can be any other variable. So, okay, this is the Fourier transform, FUV, but UV takes the value of rho and 0. Okay, so we get, for theta equals 0 case, P rho equal F rho 0. What does this mean graphically? Okay, so let's say we have a FUV, then what does this mean? This means actually V always equals 0. So actually this is this line on FUV. This line. So what we did is that we just proved one of the case theta equals 0. If we take a projection on theta equals 0 and then take Fourier transform, then it's matched to the value on the line over here. Okay, then we proved one of the case. Then by rotation property of Fourier transform, it must hold for any theta. What does it mean? This means so rotation property of CSFT is like this. For example, we have some fxy, and then there is some corresponding Fourier transform something. Okay, and the rotation property says if we rotate this fxy with a certain phi, let's say, then the Fourier transform of fxy also rotates with the same amount. That's the rotation property. So if we use this property, we are done with the proof. Because, for example, okay, okay, this is a fxy, and this is a FUV. And we already know if we take a projection onto this line and then take Fourier transform, we already know this value on this line matches to this line on FUV. And what I want to know is, what if we change the theta? For example, we want to take a projection onto, okay, this line, let's say phi. Then what we can do is, okay, look at this, and then rotate object so that this line matches to the axis x. Then this map to the value of the rotated frequency transformation line. So that means the Fourier transform of this projection matches to actually here. And then, you know, this Like we can say same thing for any angle phi. So proof is over. So actually in this proof, we just need to prove only one case. So that's the end of the proof. Okay, so we finish up the proof of Fourier Slice Theorem. And let's go back to the original part. Okay, why Fourier Slice Theorem is so important? We already learned, okay, if we use this theorem, we can plot FUV. And if we take inverse Fourier transform, we can reconstruct original image, fxy. That's very nice, beautiful. But the life is not so easy. Actually, if we use this method, there are many technical challenges to implement it. Why? Actually, we can see challenges, actually. Okay. Using Fourier Slice Theorem, actually computer can handle only discrete values. So what we can do is, we want to plot FUV using the projections. So okay, I can calculate, and then we start plot like this. Okay, then I change the theta a little bit, and then I can calculate Fourier transform of projection like this. Okay, so I just can continue, and then we can plot everything. However, next step we take is inverse Fourier transform from this capital FUV to fxy. To implement this inverse Fourier transform, what we really need is data on rectangular grid, like this. To implement the inverse Fourier transform, what we need is data on regular grid. So this point doesn't match to this one. So actually, we have this data, but we really need is the data at the location of the circle. And then to get the data on this circle location, we need to do some kind of interpolation using this cross-out data. Like you can use anything, but actually this costs a lot, like computationally expensive. And plus, look at this. Around the origin, the data is very dense. So probably, even if we do interpolation, probably we don't have problem. But if we look at these two lines, if R is getting larger, these two lines getting far away, right? Like this. So, like if you look at the data far from the origin, the data are very sparse. We don't have many data. So if we implement interpolation, maybe we don't get good accuracy. So that's another problem. So maybe in the real reconstruction, probably we can get good reconstruction in higher frequency domains. Yeah.
Why do we have a rectangular box for circle?
Actually, this is just the way like inverse Fourier transform is. Just to implement inverse Fourier transform, we need these like equally spaced samples in rectangular grid. Yes. So yeah, there are many problems. Actually, this Fourier Slice Theorem is very beautiful, but we have some challenges to implement this. So most of people don't use this direct method. Instead, most of people use this algorithm, which is called convolution back projection.